Mr. Penguin, I learned strain in a lecture of strength of materials today.
That's good. How was it?
It was very easy. If I apply attention to a material, and it stretches a little, the strain is calculated like this.
Right.
I also learned shear strain. If a material is deformed toward shear direction, the shear strain is expressed like this.
Thank you. The strains you introduced are called engineering strain.
Exactly. And the teacher introduced the authentic expressions of engineering strain. Here are the expressions. It was an easy lecture to understand.
I see. Can I give you a question about strain?
Of course.
Let me prepare a coordinate system first. I'd like you to imagine that a material has this coordinate system. Let's say, you applied a force to the material, and a point in the material moved a little, to another point like this. Can you find the engineering strain at the point?
Well, it seems like a composition of normal strain and shear strain. I'll try to find the normal strain first. I feel like I can easily find it, by using the expression of normal strain, but...
Do you have a trouble?
Yet. When I use the expression of normal strain, I have to know both amounts of the stretch and the original length, right? I think I can calculate the amount of the stretch. However, I have no idea to find the original length.
It may be necessary to define an original length, in order to find a strain. Let me explain the reason. Please take a look at this. I defined a length in a material on the coordinate system. And as you can see, this is the original length. Let's say, you applied a force to the material. The material was deformed, and so the length in the material was also deformed.
It seems like the length didn't stretch at all.
It looks so. I'll prepare another length in another material. The material was deformed, by the same amount like this.
The length stretched this time.
Yet, there are cases in which strains are different from each other, even though the displacements are the same.
I see.
Then let's try to define the original length in a material. I defined a length in a material this time. Here is the length, and as you can see, this is the original length. The material was deformed, and the length in the material was also deformed like this. Can you find the strain this time?
Well, I'd like to use these expressions, but I'm not sure how I can apply them to find the strain. I feel like the expressions are too simple to find the strain in this case. I'm going to apply the authentic expressions of engineering strain. By the way, U and V in the expressions are displacements.
Do you think you can apply the expressions to find the strain?
Well, I gave up.
I bet. Actually, we cannot find the strain at a point, even if we analyze how the point in a material moved.
What do you mean?
Please take a look at this. I prepared two of the same materials. We are going to analyze the strain at these points in the material. The materials were deformed, and let's say, the displacements of the points were the same. However, the material on the left side was deformed like this, and the other material was deformed like this.
Mr. Penguin, I realized something. The point in the left material has shear strain. But the point in the right material doesn't have shear strain.
That's right. But why do you think that the point in the right material doesn't have shear strain?
It's because the shape of this cylinder has kept its original shape. The point is not deformed toward shear direction. Now I understood what you said a while ago.
Yet, we cannot find the strain at a point, even if we analyze how the point in a material moved.
Then how can we know strain in material?
We need to know displacement field, when we try to find a strain.
What is it? Can you give me an example of displacement field?
Here is an example. You can find the strain by using the expressions of engineering strain.
Sure, it's easy. Here it is.
Thanks. Have you got along with strain?
For sure. Thank you.